Alright, now let us come to another section of this DC machine. We are still on the separately excited DC generator. What we want to talk about is about the winding inside this armature. Now you still remember that this structure is called armature, and the current that comes out from it is called armature current, and the voltage developed across it is called generated voltage, EG, right? Now what we are interested now is the conductors inside the armature. Remember, we said that there are many conductors inside the armature that's going to react with the magnetic field and therefore produce the voltage. Voltage is induced. Now, there are two types of connections of the conductors inside the armature. They are called the wave winding and lap winding. Alright, and today we want to compare these two winding methods. Now, first of all, we need to understand this C. C stands for number of parallel path. Number of parallel path means the number of parallel circuits. And P is the number of poles in the armature. It's a structure in the armature where the windings are wound together. Now, if it is done in the wave winding method, there will be two parallel paths. And if it's lap winding method, the number of parallel paths is equal to the number of poles. So in this example here, I say there are 4 poles machine, right? So there are therefore 4 paths. Now basically that's what it means. If I have 2 paths, means I'm going to have 2 parallel path circuits. Alright? That means to say in the number of conductors inside this armature is organized only in two electric paths. Alright? And each battery here represents one conductor. One conductors. Okay? And if its lap winding is a 4-pole machine, then I would have 4 paths. 1, 2, 3, 4. Alright, so 4 paths. That's the meaning of wave winding and lap winding. Okay, let's go through a simple mathematics, simple calculation to illustrate the difference between wave winding and lap winding. Right, let me erase this. Okay, so now let's talk about wave winding. Now for wave winding, the number of parallel paths is equal to 2, right? And if I were to say that the current through each conductor is equal to 15 ampere, and the voltage produced by each conductor is equal to 1.2 volts. 1.2 volts. And there is 1,000 pieces of conductor. So if it is wave winding, there are 2 parallel paths. So if I were to draw the diagram, there will be 2 parallel paths. And each small battery here represents 1 conductor. Right? So the current through each conductor is 15 ampere. 15 ampere. So the total current is therefore 2 times 15, that is equal to 30 ampere. Right? And the voltage produced by each conductor is 1.2 volts. Then we ask ourselves, in this parallel path here, how many conductors are there? There are 1,000, and I divide them into 2 groups, so each group would have 500 pieces. So there are 500 pieces of conductor, and each one produces 1.2 volts, so that is equal to 600 volts. 600 volts. So in other words, the EG is equal to 600 volts. So in this wave windings armature in my separately excited generator, the power therefore generated is equal to V times I, which is equal to EG multiply IA. So that is equal to 600 multiply 30, and that is equal to 1,800 watts. Alright, so let us remember this figure, and then we move on to do our lap winding method. So this is the wave winding method. Alright, so now let's move on to illustrate the lap winding method. Alright, lap winding method. Okay, the number of paths will be following the number of poles. So in my example here is a 4-pole machine, so it will be a 4 path. Right, it will be 4 paths. And the same characteristic, the current through each conductor is 15 ampere. the voltage produced by each conductor is 1.2 volt and 1000 pieces, right? So with this assumption, let's draw our circuit. For a lap winding, I would have 4 paths. 1, 2, 3, 4. And again, every small battery here represents one conductor. Right, so this time, the armature current, you would have 415 ampere. Because there are 4 paths, right? So the total current is 4 times 15, so it's therefore now 60 ampere. 60 ampere. And how about the total voltage here? The total voltage here, in each path, there will be 1000 divided by 4, because there are 4 paths now. So 1000 divided by 4 is 250 pieces of conductor. Alright? And each conductor produces 1.2 volts. 1.2 volts. Okay? So that gives me how many volts? If you were to use our calculator, 250 times 1.2. So that is 300 volts. So EG is therefore 300 volts. So now let's compare. For lap winding, my IA is 60 ampere. For wave winding, IA is 30 ampere. Right? And for wave winding, the EG is 600 volt. And for lap winding, the EG is 300 volt. Right? How about the power generated in this example here? The power generated is V times I again. So it's equal to EG times IA. So that is equal to 300 multiply 60, and that is equal to 1800 watts. Now you notice that the power generated for both examples here are the same. They are the same power generated, but this one has a higher armature current, but lower EG. So can you therefore conclude that for lap winding generator, you will produce a generator with a higher current, but lower voltage generated. Whereas for wave winding, you have a lower armature current, but higher voltage generated. So the choice of lap winding and lap winding versus wave winding is the choice of whether you want a high current generator or low current generator. If you want a high current generator, you would choose lap winding, right? If you want high voltage generator, you will choose the wave winding, right? And that is the comparison between wave winding and lap winding. Thank you.